Hello friends, now we are going to talk about the another topic is nothing but the power transistors, right? As we have seen the general transistor, that is NPN transistor, mostly we discuss. Now we are just trying to understand that it is meant by the power transistor, right? As we know that the power is nothing but the product of the current and the voltage, right? So the power transistors are particularly are designed uh, for power amplification or the some power switching properties, and obviously they must handle the higher amount of the voltages and or large amount of the currents flowing through it, right? So now when we are trying to design power transistors or this type of the transistors, however a trade-off between the what we can say is the trade-off between the power and the speed has to be the compensated, because what we have known about this thing is nothing but the because of the power and the frequency product is mainly limited by the its material properties, right, or some material parameters related to it. Typically, actually, this output uh, power varies over the square of the inverse proportion of its frequency. As a result of it, what we can as a result of the limitations of the avalanche breakdown field and the carrier saturation failure. So those these two important parameters are very much affecting on the its power output, right? So under the some kind of the pulse condition, the high power output can be realized, okay, into the high power output can be realized than in the continuous wave operation. Continuous wave operation something like, okay, in a continuous manner we can try to provide the power to the particular devices, right? So in the pulses form or also in the continuous wave operation. So let's try to understand that the some example, right? If suppose we are trying to give us the more amount of power, then it has to be obtained, that higher power can be obtained at the very lower frequencies, right? So or in the pulse formation, something like a 500 watt of the power can be obtained at the 1 gigahertz for the pulse operation. Or else if we just trying to understand that for the continuous operation, if we want to have the continuous operation power transistor, then the low power will be obtained at the higher frequency, something like 60 watt can be obtained at the 2 gigahertz, and so on and so forth. And if we just try to reduce the power by some fraction, then 1.5 watt can be obtained at the 10 gigahertz, can be easily achieved, right? So let's try to understand that what is meant by the high voltage limits here. So the high voltage operation is limited by the its breakdown, okay. Typically this value at the offset is given by the, as we can see, is the VBCEO at the emitter. How much is the base to collector potential is applied at the offset, okay. So is given by, and already discussed before as well, the breakdown voltage is higher if the current gain is lowered one. So for this reason it is always advantageous to degrade the current gain in order to extend the voltage range, right? So if we want to extend the voltage range, obviously the gain has to be degraded. So this is another approach to add an external resistor, okay. So there is another approach to add an external resistor between the base and the emitter to degrade the current gain as well, right? Even we can discuss the another effect, that is high current effect. So what happens that when we are trying to apply the high currents, right? So under this there are many undesirable effects observed through it. So just like wide base widening due to the Kirk effect, or else because this is what we have seen in the Kirk effect, right? So the base can be widened, or the current crowding toward the boundary of the emitter. Okay, current crowding, so the current will be crowded at the emitter because of the intrinsic base resistance is another factor which affects on it. Also, in order to obtain very high background voltage or breakdown voltage, the collector doping must be reduced, or else the low collector doping not only exacerbates the Kirk effect, also it induces the region of the quasi saturation due to the conductivity modulation in the collector. Okay, so if you try to understand that the further the region of the quasi saturation, you can just try to go through the book. You will get the idea about the what is meant by the quasi saturation and the other some effect like the saturation and the normal mode of the operation in the SMG's book. Okay, now in continuation with that, we will try to understand that the main effect is nothing but the second breakdown, which is quite important topic to understand the things related to the power transistor. So in this second breakdown is quite important thing. So what is in the region of the high current and the high voltage. So here we are considering the very high current as well as the high voltage. So the power transistors are often limited by the another phenomena, we call it as the second breakdown. Okay, which is marked by the okay, so this is marked by the what we can say, the abrupt decrease in a device voltage with simultaneous internal constriction of the current. So this background effect this breakdown phenomena is observed by the earlier by Thornton and the Siemens, right? So has since under the extensive studies in a high power semiconductor as well since its invention, right? So for a high power transistor, what is the requirement or the operation criteria is must be operated within the certain shape region. Okay, certain shape region, so that the permanent damages can be avoided, which is caused by the second breakdown. Okay, so now in this figure we can see there are 4 stages of the operation of the this breaking down happening. It's the first breakdown and the second breakdown. So in the you can see the 4 different regimes through it, right? So in the first stage, what happens that leads to the instability of the current at the background stage. So here the instability happens. In the second stage, what happens during this this is something like okay, in the second stage, in switching from the high to the low voltage region, right? So this is a high voltage region and it is just switching to the low voltage region. Okay, and in the third stage, what happens that again the third stage over here, that is going to the low voltage to the high current. So the low voltage to the high current is happening, and in the fourth stage, what we can say, there is a permanent destruction of that particular transistor. So this happens that, so there are the general features of the common emitter characteristics under the second breakdown conditions. So what is it actually? The what we call it as the avalanche breakdown. Okay, avalanche breakdown. Okay. Suddenly the current is increasing. So this is avalanche breakdown. Okay, occurs when the applied emitter collector voltages reaches the value of the earlier whatever we have seen is the VBCEO. Okay, as the voltage again the further increases, then the second breakdown occurs. Okay, so the voltage, if you just try to increase, a second breakdown occurs. Okay, and then the experimental traces generally consist of the 4 stages that already we have discussed. These stages occurs further, and the complete destruction of the transistor happens at the after the fourth stage. So during this, what happens that after the instabilities, okay, so here the instability of the transistor happens and the voltage collapses across the junction. So during this second stage, what we can see is the background breakdown process occurs. Okay, the resistance of the hotspot becomes drastically reduced. Okay, here how it is reduced, because voltage is decreasing and the current remains the same. So obviously the its resistance drastically becomes reduced. Okay, in the third stage, what you can say, the low voltage and the high current stage. So the semiconductor is at the high temperature because of the high current, and uh, is intrinsic in the vicinity of the background spot. So it becomes intrinsic in the vicinity of the background spot, and as the current continues to increase further, so the background spot melts and results into the fourth stage of the destruction of that particular transistor. Okay, so if we want to understand that its real application, try to read the SMG's book, and you will get the idea about the how it is helpful in real life applications.